Hey guys, Kendra this side. And this session is very important, though you may feel that we know already what is meant by charge, or what is meant by current, or what is meant by power, what is meant by energy, electric field, magnetic field. But I know, like, in basics, we should be so strong. Then only in further application stage of basics, kind of machines or power systems or power electronics, dots will be properly connected. So this session, because we are going to deal in altogether different way. Anyway, before starting the discussion, let me share details about myself. I'm Rao, and I got more than 20 years of experience. By GATE 2021, I completed 20 years of GATE training. Okay, and I worked in all prominent institutes, kind of made easy arrays. And obviously, I should have 1 lakh plus members, obviously, because 20 years. And subjects, as of now, I'm planning machines, network theory, and in future, I'm going to include power systems also. And if you want me motivated, please like, share, subscribe to this channel. And if you want me motivated, use my KNR10 code. Obviously, more responsibility will be there on me the moment you use my code. And here there are two types of courses in Unacademy paid platform. One is Plus, another one is Iconic. In Plus, you are going to get live courses, live classes. You are going to get crash courses. You are going to get weekly tests, doubt solving sessions, and rank improvement batches also will be there. And if you think of actually that Iconic subscription is superset, is big. In Iconic subscription, extra whatever you are going to get in Plus subscription, you are going to get Iconic also, and extra you are going to get kind of personal coach. Okay, the moment personal coach is of your age and who is an already an achiever, obviously personally he is going to guide you. And in lot of times, the moment you get demotivated and all, that help is very much important. And the personalized test analysis will be there, kind of study material will be there extra in Iconic, and also study brochures series will be separate, that will be provided. And the next thing is subscription prices. For Plus, if you use my code KNR10, you are going to get it for 27,225, and easy EMIs are always available. And this is for 12 months subscription, and for 18 months 34,650. And with my code KNR10, all of us know that 10% discount you are going to get. And with KNR10 for 24 months, it is going to be 39,600. And if you think of Iconic, in Iconic, this is 40,500 for 12 months and 54,000 for 24 months. Okay, and for third years, it is recommended to take 2 years course. Okay, and yeah, they thought of increasing the price hike they planned from July 1st onwards, but because of lot of demand, they stopped that, they postponed that. But very soon prices may be hiked. And here there are two types of batches, Lakshya and Arohan. Lakshya batch is meant for GATE ESE 2022, and Arohan batch is meant for 23. In the sense, kind of 2 years batches, 1 year batches, kind of stuff. And in electrical, obviously all prominent faculties, Varun Srivastava sir is there, Vishnu sir is there, and many of the members worked with me previously. They are very prominent and top faculties. And on July 7th, one more batch is, they are going to start one more batch. So try to take subscription. And for ECE, these many members will be there. Next thing is test series. For test series, of course, they are providing free test series, and obviously they will provide extra for the Plus subscription, extra test series, kind of accelerate, elevate, excel, accord and all. And here, yeah, every Sunday combat will happen, but this Sunday, coming Sunday, date I don't know, coming Sunday, this is actually very big because scholarship of 4 crore, and the toppers are going to get free subscription for GATE and ESE, 1 year subscription they are going to get. If you top, it would be great. And remaining guys also are going to get some kind of concessions, some percentages. And here you are going to get, for some lucky participants, will get a chance for the surprise gifts also. Okay. Oh, this is new. And follow me at KNRAO for you, KNRAO number 4U, such that you will get notifications whenever I come to live and all in Unacademy platform. Now, let us start. See here, what is meant by charge? Okay, everyone know. But let us understand a bit different way and a more appropriate way, such that it will be connected in our machine power systems, or kind of what do you say, application oriented subjects. Okay. Now, first of all, notation has to be understood. Okay. If you think of notation, we are going to follow one notation. If I think of current, already you know what I mean by current. Outline at least you know. So if I think of current, normally current we are going to represent with letter I, right? So I can use I also, small I also, I can use capital I also. Where small I has to be used, where capital I is supposed to be used. If you see here, if I think of any kind of instantaneous varying signal, let me think of sinusoid, or let me think of triangular, whatever it may be. Okay. In this way, for example, if this is current, we are going to use small case letter. We are going to use small case letter. Okay. Of course, this is going to be time. With respect to time, we are going to use small case letters. That is the standard we are going to follow, and Hythen Gemelli followed same. And the next thing is, if I have constant DC, and I will tell you what in even though in this particular time varying fields also, okay, or time varying current or time varying voltage also, sometimes we have to use capital letters only. Those things also we are going to discuss. Now, the moment it is current again, why I said small case letter is going to be like kind of superset. Now this is current, this is time. Okay. Now this is going to be constant current. So the moment it is constant, I can say I equal to 10 amperes. Or anyway it is constant. No. The moment it is constant, I can use capital I of 10 amperes also. Okay. One thing, whatever is constant invariant, okay, we are going to use capital letters. Even if you think of, normally in network theory, we don't use small case letters of small r, small l, small c normally. Okay. So if I think of resistance, normally we represent with capital letter. Okay. If I think of inductance, normally we represent with capital L, because already in our previous session we discussed it, right? So time invariant elements, and a time variant input output, excitation, responses and all. Normally we are going to use capital letters here because they are time invariant over the time period we discussed. Now here also see here I equal to 10 amperes, which is constant we can say, or capital I equal to 10 amperes, which is time invariant over the time period. Now let us come to here. This is time varying. For example, let us think of maximum is maybe 10 amperes. This particular maximum value is 10 amperes. Then what I can write here in order to represent this current as I of t equal to 10 sine omega t can be represented. Okay, we have to use small case letters only. Now, if you think of capital letters in time varying current, how to represent? What is time period here? Time period is this. Okay. See, even in time period representation also, capital T we are going to use this for time period, and small t we are going to use for in order to show that time varying current. Okay. Anyway, point here is, for example, over the time period, whatever are constant values, average value is going to be constant, right? Average value over the time period you have to consider. Over the time period, the average value is constant. Over the time period, RMS value is going to be constant. How to calculate RMS value? What is RMS value? Those discussions we will see later. Okay. Now, average value, for example, for a sinusoid, over the full time period, the average value is going to be 0. In order to represent that, capital I only has to be used. Of course, for half of the time period, some other non-zero value will come. It's a different story. But for full sinusoid, we know that, right? Average is going to be 0. Now, RMS value. For RMS value also we have to use, because RMS value over the time period is going to be constant. Okay. So this is the representation. Small case letters, it can be current, or it can be voltage, or it can be power, instantaneous power. If you want to represent, we are going to use small case letters. Over the time period, whichever may be the constant, kind of average value. Okay. Or maybe RMS value. Okay. Or over the time period, we are going to use capital letters like that. Now, next thing is, this is just the notation. Now, let us think of charge. Okay. If you think of charge, because by this discussion, you will come to know that kind of you can connect some dots that why capacitance value always will be in microfarads, picofarads. Why can't it be in farads? Okay, of course, maybe in diploma level books, they may give you, in order to simplify the question, they may give you 1 coulomb of charges here, 5 coulomb of charges here, but coulomb is very big number. Okay, why capacitors cannot have cannot have coulombs or cannot have farads. Okay, directly 5 farads of capacitor, 10 farads of capacitor, we cannot get in the practical world. Why? You are going to get the connection from here. Now, what is meant by charge? Of course, people will directly, derive this charge from current. Okay, but I don't want to do that. Directly only I want to go. Now, see, it can be small q, time varying, or it can be capital Q, time independent over the time period. Okay. Now, point here is if I think of a charge. Okay. So we know already this particular equation we know from long back. Q1 Q2 by this square, right? Force between the charges, attraction force or repulsion force. Already we know same charges will repel each other, opposite charges will attract each other. These kind of stories already we know long back, right? Now, what this particular proportionality constant, if you keep, it is going to be 1 by 4 pi epsilon naught in free space. Other than free space, epsilon r also will come, you know. And this is going to be Q1 Q2 by d square. Okay, if you keep this epsilon naught value and all, it is going to be 9 into roughly 10 to the power of 9 Q1 Q2 by d square. It is going to be force. Okay, now already we know that if I have two charges here, okay, so for example, this is a standard static Q1 charge and standard static Q2 charge. Then between these two charges, we are going to get opposition force, repulsion force. So here, repulsion force will be there. Or upon this, in this direction, repulsion force will be there. Right? Now, if Q1 and Q2 are equal charges, displaced by 1 meter, and if repulsion force is 9 into 10 to the power of 9 Newton meters, that means that those particular equal charges are going to be 1 coulomb. Okay, let me tell you. For example, if I think of this is 1 coulomb, this is 1 coulomb, and this is 1 meter. Then how much force will come? That force is going to be 9 into 10 to the power of 9 Newtons. Meaning that, for example, if repulsion force, if you measure for equal charges, okay, equal and same charges, equal magnitude of charges, and provided that particular distance between the charges is 1 meter, then if you measure that particular force is 9 into 10 to the power of 9, very big number, 9 into 10 to the power of 9 Newton, then I can say that Q1 value or charges values are going to be 1 coulomb. Okay. Now, see on this number, 9 into 10 to the power of 9 Newtons, not a small number. Meaning that means 1 coulomb we cannot keep. Okay, this is from definition point of view. If you keep 1 coulomb here, and distance between them is 1 meter, then automatically force will be very short. So the moment force is very short, practically we cannot have, right, that much huge force. So means it cannot be this much. Meaning that this particular Q values cannot be that much. Meaning that directly this can be connected to capacitor. Magnitude of capacitor cannot be in farads and all. It can be in microfarads, picofarads only. We can design in practical case. Okay. Now the same thing we can conclude from another way also. Okay. So in another way, if you try, kind of electron. Okay. So one electron charge, you know, I know that 1.602 into 10 to the power of minus 19 coulombs. Okay. Of course, we say it as negative because one thing I'll tell you, in practice, we know that proton and electron are having opposite charges. We know only that because electron is a physical entity. Okay. You cannot provide negative for it. But the moment they are having opposite charges, In converting mathematical means if you keep L for electron negative, automatically proton will become positive. That's it. Okay. Now, from this point of view, what is meant by 1 coulomb? 1 coulomb. 1 coulomb. Meaning that 1 divided by 1.602 into 10 to the power of minus 19 electrons. Okay. Meaning that roughly something will come here and at least 10 to the power of 18 electrons will come. Okay, 1 by 10 by 1.602, somewhere around 1 by 10 by 1.6, maybe roughly 8 or 7, something like that. Okay, so 10 to the power of 18 electrons you have to remove from my material in order to make it 1 coulomb. Again, which is very big number. Okay, so if I have material here, 1 meter cube of material or any size of material, you have to remove how many electrons? 10 to the power of 18 electrons plus you have to remove, then only it will become 1 coulomb of charge. So 1 coulomb is very big number, very big number. Okay, now let us think of current, and one advantage is there for current apart from voltage or magnetic field apart from electric field. I'm going to discuss soon. Now if you think of current, what is current? Rate of charge is nothing but current. Okay, so stay tuned. We are going to discuss very beautiful things in the discussion of voltage. Okay, now for example, if I have one conductor here and if I keep on inject current here, now where I'm going to set? Somewhere here I'm going to set. Somewhere here I'm going to set. And whatever will be the charges crossing me, I'm going to count. And how many charges cross per second? Rate of charge. Okay, rate of charge is nothing but current. So I is going to be dq by dt. dq by dt is going to be the current. Okay, now means we are going to come back to this particular situation again. Okay, but let me enter into voltage first, because from voltage only we can connect that particular voltage discussion to KVL, conservation of energy, electric field, magnetic field, equipotential points, many things we can discuss. Okay, now let us think of voltage. What is meant by voltage? This is very important discussion, and many guys will have that doubt also. Like, what is voltage? What is voltage? Because current in the sense we can visualize, right? Some electrons are flowing like this. Okay, negative electrons are flowing from from here to here in this direction. Meaning that if we assume positively, the positive current is flowing from this to this direction. We have at least. But what is voltage? See here, very simple. We have to just connect that to the gravitational field. If you connect voltage, electric field to gravitational field, it is going to be dead easy. Now, see here, if I have one charge here, then around the charge, you are going to get electric field or not? Yes. So that electric field will be in this. Okay, electric field is a divergent field. In this is field means field spread will be in this direction like this. Okay, in all directions. Electric field is a divergent field. And if you think of magnetic field, it's a curly field. Okay, maybe if I think of one conductor is there like this, current is flowing in this direction. So my magnetic field is going to form closed loops around it. Magnetic form is going to form curly field. Okay, or let me take directly N as poles. We know this from our 10th standard only. From N, flux will come like this in this direction, inside S to N, and inside S to N, outside N to S. Okay, so always magnetic field will be formed in closed paths, meaning that curly field, and electric field is divergent field. Okay, now forget about this. Now, if I keep one more test charge here, you have to focus here only, dear. Okay, if I keep one more small test charge, this is very big charge, such that presence of this charge. Actually, there is one small assumption here we have to discuss. Okay, normally if I keep that assumption you have to understand. Okay, and if I have if charge is not there, then how my field structure will be? Field structure will be like this. Now, if I keep one more charge in the vicinity of this charge, so if I keep one more charge here, okay, one more charge in the vicinity if I keep, then what will happen? My electric fields, they will change their path. Meaning that presence of this particular charge changes the flux pattern of this or not. Okay, from this directly we can connect to what do you say, dielectric pole and all, dipole and all we can connect, but for time being leave about it. So if you keep one more charge in the vicinity of this charge, my electric field flux pattern is changed or not? Yes. Why the flux pattern is changed? Maybe discharge and discharge magnitudes may be comparable, and if the distance is close, a kind of dipole kind of stuff. But now my assumption, okay, in discussion of this particular voltage is this is very big charge and this is very far away, such that even though small test charge is there here, this will not disturb the flux pattern, electric flux pattern of this particular charge is my main assumption in defining the voltage. Okay, process we have to enjoy. Let us go slowly, okay, because the basic should be very strong. Okay, now coming to this point, see here flux pattern is as it is. Then let us focus on this particular test charge only. Okay, if you focus on this particular test charge, then definitely on this test charge, because of the presence of this particular main charge, some force of repulsion will be there. Okay, some what they say mechanical force will be developed in this direction, right? Now if I want to keep this charge here only, what I am supposed to do? Obviously I have to apply some applied force. That applied force magnitude should be equal to repulsion force, right? If repulsion force equal to applied force, then only stable operating point will come and this particular test charge can stay here only. Okay, for example, if I don't apply this particular force, then because of only repulsion force, charge will go away in this direction. But I'm saying charge is going to stay here only. What does it mean? Meaning that some applied force exactly equal to repulsion force is applied in opposite direction. Now, see here, some repulsion force is there in this direction. And on opposite direction, some applied force is there. So, in order to keep the test charge, focus, relax. Now, means you are applying some applied force. Are you applying energy or not? Remember, right? You are applying some force, but are you supplying any energy here? Okay. For example, if I stay like this here, okay, I applied some force on this particular chair. I applied some force because I'm bending. No, I'm applying some force on this particular chair. But am I supplying any energy? No, because what is meant by energy? Force multiplied by distance is energy. Okay, force multiplied by distance is energy. But here you are applying only force. Okay, and that particular force variation is not there, just a force is there, and without moving any distance. So you are not going to get, you need not supply any energy, but you have to supply only force. Getting my point, right? Now, if I think of in this particular situation, you need not supply energy. Now, if I want to move this particular test charge from here, let me think of this as point 1. And from point 1, if I want to move the test charge to point number 2. Try to understand two things. First of all, if you compare the magnitude of repulsion force here and magnitude of repulsion force here will be more. Why it will be more? Because distance is reduced, Q1, Q2 by d square, directly proportional to the d is the distance between the charges. So here, you are going to get more repulsion force. Okay? In order to keep the test charge here only, you have to apply more applied force. Okay? Now, see here, focus on this particular movement. Then you will understand from Maxwell's equations. Actually, in EMF, first electric field, static fields, then magnetic fields. After that, Maxwell's equations will come. Maxwell's equation, this is interaction of electric field and magnetic field, you will understand now. Okay? Why? Because for energy transformation, with only electric field, you cannot transform energy. With only magnetic field, you cannot transform energy. But interaction of these two fields are required. Okay? Now, see here, for example, here, my applied force is there. For example, repulsion force is in this direction, and my applied force is in this direction. It is stable there. Now, gradually, I am moving towards this too. So while moving, what will happen? My force of applied force should be more because repulsion force is becoming more. Okay. Now, means force variation is there. And also, you are moving towards some distance from position 1 to position 2. Definitely, you have to expend energy or not. Yes, right? See, for example, repulsion force is in this direction. Applied force is in this direction. Just applied force, it's okay, not energy. But my applied force is more compared to repulsion force, then only I'll be able to move like this. The same concept I'll discuss in motors and generators. Same, everything will be same. Okay. Now, for example, means okay, let me think of this as weight, mass. Consider calculator. This as mass. Okay. This mass is in the ground floor. This is ground floor, let us assume. And I'm pushing this particular mass towards first floor. I have to expend energy or not? Yes. Yes, right? Because from here to here means from ground floor magnitude of applied force to first floor magnitude of applied force should be more. Getting my point, right? So here, see, here applied force equal to repulsion. Okay, applied force is going to be more here. Now, while moving from here to here, while moving from position 1 to position 2, as applied force should be more here, applied force should be less here, definitely you have to expend energy. Now, for example, from 2 to 1, if you are moving from 2 to 1, okay, if you are moving this particular test charge from here to here, okay, so definitely what you're supposed to do while doing from here to here, your applied force has to be reduced to less than repulsion force such that you'll be traveling from here to here. And again here, in order to keep it here only, means again applied force should be equal to repulsion force of these magnitudes. Now, maybe in all over world, we are generating these many gigajoules of energy, right, at generating stations. Why we are generating these many joules of energy? Because those many joules of energy has to be consumed by the consumer, okay, such that for that, for that consumption, he is going to pay money. With that money, generation will be able to generate power. Okay. Now, these many gigawatts of power all over world, in all countries, means they are generating such that that particular power has to be consumed by someone. Okay. Otherwise, what is the purpose? Now, see here, everywhere power transformation is important, energy transformation important, because energy is being created, electrical energy. Of course, I'll tell you the differences also later. Okay. So, that particular electrical energy is created at generating stations such that it should be consumed by the consumers. So, this is the main purpose of complete power system, right? Now, point here is energy. In order to transform energy, what are the things which are required? Let us see. Okay. Now, see here, first point. This particular test charge is here. Applied force equal to repulsion force. This is stable. Are you supplying or are you transforming any energy? No. Right? You are not transforming any energy. Now, by keeping at first position. Now you are traveling from first to second. Okay? Meaning that you are spending energy. Okay? You are spending energy in moving this particular test charge from position 1 to position 2. Okay? Now after that, if you release this particular 2 and if you catch the same at position 1 because of this repulsion, whatever the energy expended will be delivered. Right? If energy expended equal to energy delivered, what does it mean? That is conservation of energy. Now, see here, if I think of this as the mass, okay, with this, with gravitational field, if you connect, it will be very easy. Okay, and of course, some contradiction also will come in the next session. This session only, I'll try to clear that. Now, this is mass. This is at ground floor. Now, in order to move this mass from ground floor to first floor, I have to spend energy. I have to expend energy. And from first floor, if I drop same amount of energy will be delivered. So means this is going to be conservative field. Okay, that's why wherever conservation of energy is valid, we call that field as conservative field. Here also, as electric field is conservative, because for conservative fields only we developed EM theory concepts and all. If any field is not conservative, we cannot do anything that way. Get my point, right? If any field is not conservative, meaning that we cannot apply our physical laws at all. Kind of black holes. Okay. Now, see here, as electric field is what they say conservative. Whatever may be the energy you spent in shifting the charge from here to here, and whatever the energy you are going to get back in shifting the charge from here to here, both are same. Both are same. Okay. Now, let us directly connect this to KVL directly without even what they say defining voltage. See here, if you are moving from here to here, you have to spend energy. In moving from here to here, that energy will come back. Such that what is the net amount of energy in shifting the charge from here to here to here to here to here to here is going to be 0. Now, why to go like this? Let me go randomly, such that let me go like this. Okay, at one point, if you are moving towards the main charge, you have to spend energy, and if you are moving far away from main charge, it is going to deliver energy. Now, if conservation of energy is accepted here, conservation of energy should be accepted here also, right? Because it's a closed path. Now, let me tell you, in any closed path, independent of the path followed, energy is going to be conserved. Okay, or the moment energy is conserved, meaning that energy expenditure should be equal to energy delivered. Okay, so it means let me say here again, in any closed path, independent of the path followed, energy expended should be equal to energy delivered. That is nothing but Kirchhoff's voltage law. Kirchhoff's voltage law is derived from conservation of energy. Okay, keep that point in mind. Now, anyway, which is at higher potential, which is at lower potential, and directly let me connect this with voltage. See here, again mass. This is ground floor. This is first floor. Now, if I expend energy, it will reach to higher potential. If I take back energy, it will go to lower potential, gravitational field, right? If I expend energy, it will go to higher potential. If I take back energy, it is going to become lower potential. Keep that point. Now, let us apply the same here. Okay. Now, let me write this. Now, okay, means in moving from 1 to 2, I am going to expend energy. In moving from 2 to 1, it is going to give back the energy, deliver back the energy. Meaning that it should be higher potential, it should be lower potential. It should be lower potential, it should be higher potential after comparing with gravitational field. Now, what is meant by voltage? Okay, voltage means energy expended per coulomb of charge in moving the test charge from one position to second position. That's it. Okay, let me repeat again. Voltage. It is now, you should not think of directly voltage at all. It is not like that. See, voltage means energy expended per coulomb of charge in shifting the charge between two distinct positions. Okay, meaning that if I am moving my charge from here to here, means we have to expend energy. That expended energy per coulomb of test charge is nothing but voltage. Now, what is the dimensions? Dimensions are important. What are the dimensions? Energy expended per coulomb of charge. In SI unit, it is equivalent to volts. That's a different story. Okay. Now, this is going to be about voltage. Now, see here, let me directly again connect this with KVL. Okay, a lot of discussion is going to happen on this particular area because it is required. Okay. Now, point here is, see here, if I move my test charge from here to here, what is happening? If I move my test charge from here to here, I have to expend energy. When you are expending energy, you are moving the test charge from lower potential to higher potential, right? If you are moving from lower potential to higher potential, you have to expend energy. From higher potential to lower potential, it is going to deliver back the energy, right? Now, if I say energy means in any closed path, independent of the path followed, energy expended equal to energy delivered, and energy will be expended for voltage rise, energy will be delivered for voltage drop. Of course, there is a small contradiction, people may feel. I'm there. Okay. Now, see here, energy expended equal to energy delivered, meaning that voltage rises equal to voltage drops, which is nothing but KVL. Right? Now, let us analyze this from field's point of view. Field's point of view. Let me keep here. Now, there is one concept that whenever you find electrical current around that, magnetic field will have to be formed. Okay, whenever you have electrical current, associated magnetic field should exist. Okay, maybe converse may not be true. Whenever you have flux, current may not be there, because if you think of permanent magnet, okay, if you think of permanent magnet of N pole S pole, magnetic flux will come. But where is the current? Where is the current? Okay, but whenever you have current, associated magnetic field should exist. Okay, that is keep it aside. Okay, now anyway, coming to here, if I'm moving the charge, focus here, focus. If I'm moving the charge from here to here, if I'm moving the charge from here to here, charge is getting movement or not? Because of the movement of charge, current will come. Because of current, magnetic field will come. Okay, now if I am moving from here to here, magnetic field will be formed. Or in moving from here to here, magnetic field will be formed. Right? Now, whenever current is there, magnetic field will be formed. And in moving from here to here or here to here, energy, transformation is happening or not? Yes. So, in moving from here to here, energy transformation is happening. Now, point here is voltage is there or not? Yes. Okay. Or electric field is there or not? Yes. For example, if I keep the charge here, static, without any movement, then what will happen? Only electric field will be there. With only electric field, will there be any energy transformation? No. Now, if I have both electric field and magnetic field, because if I'm moving this particular charge, it is nothing but current, dq by dt. So, if I'm moving my charge from here to here, my electric field is there or not? Yes. Magnetic field will be developed or not automatically because of the current? Yes. Because of that, energy transformation is happening or not? Yes. Okay. Now, let me extend this to equipotential points. Okay. See here, if the distance between these two, if the distance between this and this is d, and by taking this as the center, let me take an arc from here to here, such that distance from here to here is also d. Now, let me move my test charge. Let me move my test charge from position 1 to 1 dash. Okay, then what type of fields will be there? Because after this, we are going to get a beautiful conclusion. You would enjoy. Now, see here, if I am keeping the test charge here, distance is d. If I am moving the test charge here, again, along the arc only, by taking this as the center, arc, that way. Then, whatever may be the repulsion force here, same repulsion force will be there here or not? Also or not? Yes. Okay. See here, whatever the repulsion force is happening here, same repulsion force will be there here also. In the sense, in order to keep the test charge here, whatever may be the magnitude of applied force here, whatever may be the magnitude of applied force here, same magnitude of applied force has to be applied. Now, see here, if I am moving the test charge from here to here in this way, then what's going to happen? Will there be any current or not? Yes, obviously we will have current, right? In moving the test charge from here to here, we are going to have current, meaning that magnetic field will be there. Whenever I is there, automatically flux will come, magnetic field will come. Okay, so if I move my test charge here, from here to here, if I am moving, okay, while moving the test charge, automatically current will be there, automatically magnetic field also will be there. Okay, magnetic field is curly field, electric field is divergent field. Now we can form one conclusion, beautiful conclusion. That is, see here, if I keep the test charge here only, static, will there be any electric field or not? Yes. Will there be electric field or not? Yes. Is electric field divergent or not? Yes. Will there be any energy transformation? No. Now, if I am moving the test charge from here to here, electric field is there or not? Yes. And while moving, magnetic field will come or not? Yes. Okay. So, in order to transform energy Electric field should be there and magnetic field also should be there. Because of interaction of electric field and magnetic field only, we are going to get kind of energy transformation. Okay. Now, if I keep the test charge here, for example, if I keep as it is, will there be electric field? Yes. Will there be magnetic field? No. No movement of charge. Will there be any kind of energy transformation? No. While moving from 2 to 1, you are going to get energy transformation. Because while moving from 2 to 1, electric field is there, magnetic field will be there because of charge movement and interaction of these two will happen. And now, if I move from here to here, will there be any energy transformation? No. Why? Because force difference is not there. So energy you are not supplying. Energy transformation will not be there. But will there be magnetic field? Yes. Okay. Will there be any interaction of electric field with this? No. So conclusion here is very simple. In order to transform energy, means I'm not thinking about signals or signals of information signals and all, because my focus is power. Okay. Now, point here is in moving means if I have only magnetic field, nothing will happen. Only electric field, nothing will happen. If I have electric field and magnetic field combined interaction, then only we can transform energy. Now let us split this. In order to transform energy, electric field and magnetic field should coexist. Or in order to transform energy, both voltage and current should coexist. Or in order to transform energy, both divergent field and curly field both should exist. Then only we will have a transformation of kind of energy from where Maxwell's equations will start. Okay. Now let us think of KVL again. Okay. If I think of KVL again, let me think blue. Okay, fine. Okay. If I think of KVL again, see here, in moving from here to here, it is going to be voltage rise minus 2 plus. In moving from here to here, voltage drop, because you are moving your charge from higher potential to lower potential. If you are moving from lower potential to higher potential, your charge, you have to expend energy. And in moving from higher potential to lower potential, it will deliver energy. So, see here, independent of path followed. In any closed path. Okay, means net amount of energy will be 0. Or energy expended should be equal to energy delivered. When you are going to expend energy, voltage rises. When you are going to deliver, when it is going to deliver energy, for voltage drop. So expended energy should be equal to delivered energy, meaning that expended. Okay, voltage rises should be equal to voltage drops. That is nothing but Kirchhoff's voltage law. Okay, now see Kirchhoff's voltage law. Okay. Now point here is some of the students will have one doubt. Okay, and that is kind of in interviews also they will ask, if I connect 2 voltage sources in parallel with different voltage magnitudes, what will happen? For example, this is 5 volts, this is 10 volts, just like that. Then how much will be the net voltage? Okay, this is in ideal systems. Of course, developing this kind of system practically it's impossible. Okay, don't think that like 5 volts battery you are going to take, 10 volts battery you are going to take, you are going to connect these two. Then whatever may be the voltage should be this voltage. No, because these are ideal. Okay, even 10 volts ideal voltage source in practice, 5 volts ideal voltage source in practice cannot be connected in parallel. Okay, whatever it may be, if you try to apply KVL here, okay, this is 1 point X, this is 1 point Y, and equipotential points, right? Just now we have seen equipotential points. So this point is going to be Y only equipotential point, or Y dash, 1 dash we have taken now, and this is going to be Y only. Now, if I move in this way, minus 2 plus voltage rise, equipotential points, voltage drop, equipotential points. In this case, voltage rises are not becoming voltage drops. So KVL fail. Now, as KVL fail, because voltage rise is 5 volt, voltage drop is 10 volts, they are not equal. Now, can I say, so-called as KVL failed, so-called Kirchhoff one guy failed? No. We derived KVL, Kirchhoff derived KVL from conservation of energy. At any point of time, if you get this particular doubt, how much would be the voltage? We cannot say that. Because if you are having in this kind of system, in this kind of system, obviously we cannot say because it is not following conservation of energy. If conservation of energy is not followed, forget about KVL. Okay, KVL is derived from conservation of energy, right? If conservation of energy fails, our EM theory will fail, because means our main assumption is electric field and magnetic fields are conservative fields. Getting my point, right? So the moment they should be conservative, meaning that we cannot create such a situation or we cannot answer such a situation. If they are practical batteries or voltage sources, what has to be done, we will see later. Now, let us think of power. Okay. Now, from dimensions, I am going to derive for time being. It's enough. Now, let us think of power. Okay. What is the definition of power? Means a rate of energy transfer. In the sense, joules per second. Energy transfer, rate of energy transfer. So, power is nothing but how many joules of energy is being transmitted per second. Per second. Now, let us think of voltage. What is the dimension for voltage? If you think of dimension for voltage, is going to be joules per coulomb, right? How much amount of energy is being transformed per coulomb of charge is nothing but voltage. Now, let us think of current. What is current? Coulombs per second, rate of charge. Okay. Now, if I say voltage multiplied by current is going to be, from dimensional point of view, joules per coulomb multiplied by coulombs per second. This is going to be joules per second. Okay, joules per second is power. Now, P dimension should be equal to voltage multiplied by current. Voltage, of course, passive sign convention will come. Okay, and whatever discussion we had here, it will contradict passive sign convention. Kind of, for example, if charge is going from higher potential to lower potential, see here, charge is going from higher potential to lower potential, energy is being delivered. But in passive sign convention, we say that energy is going to be absorbed. Okay, means from higher potential to lower potential, if charge is moving from here to here, we say in passive sign convention, about to come in the next session, we say in passive sign convention, energy or power has to be absorbed. But here it is delivered. That contradiction in the next session we will see. Okay. Now, means even if you derive also, some proportionality constant will be there. Ultimately, that proportionality constant will become 1 only. Okay. So power, we can write it as voltage multiplied by current. And there will be so many other doubts kind of for voltage. Okay. Polarities we have to specify, right? For example, for a battery, we need not specify polarity because the bigger one is going to positive, we know, or at least plus minus we are going to specify. Okay. Now, for AC voltage source, okay, at some point of time, this is higher potential. After half of the cycle, this will become higher potential compared to this. Now, should we keep plus minus terminals or not? Yes, compulsorily we have to keep. For all voltages, we have to provide plus minus polarities at any cost. Now, if you think of current, okay, for current, direction of current is very much important. From which direction to which direction it is going is very important. And for power or for voltage, polarities are very important. Means for DC also you have to provide plus minus symbols. For AC also we have to provide plus minus symbols. And contradiction I'll tell you later, but let me tell you this. See here, everything, this figure only. Okay. Now, see here, if you are moving, okay, if you are moving from lower potential to higher potential, you have to expend energy. From higher potential to lower potential, it will deliver energy. Okay. Now, if you don't have plus minus, because in our practical system, we don't draw all this stuff. No, directly we are going to represent with the network. Okay. Now, in a network, for example, if I say this is one system, across this is voltage. I didn't specify plus minus polarities. Okay. If some current is going in this direction, is it going to absorb power or deliver power? Because from lower potential to higher potential, some one direction of power, and higher potential to lower potential, another direction of power. Now, if I don't provide plus minus polarities, how can we say? Okay, so for all voltages, plus minus polarity should be specified. Now, let us think of current. About the contradiction, I'll tell in the next session. Okay, now if I'm moving in this direction, maybe power has or energy has to be expended. In moving in this direction, energy will be delivered, right? But if you don't know the direction of current, how to say whether power is being absorbed or delivered? Okay, now see here, for all currents, direction is compulsory. For all voltages, polarities are compulsory. Without polarities, voltage should not be designated at all. Without directions, current should not be designated at all. Okay. Now, next thing is, I thought of telling something, I forgot. Let me see. About this contradiction, I'll see in the next session. I'll tell in the next session. And okay, in the next session we'll see. But compulsorily for AC also plus minus polarity. Yes. For example, if I give a battery, okay, if I don't keep plus minus polarities or if I don't give direction for current, it is how much foolish it is, I'll tell you. If you take a battery or if you take a generator directly, okay, electrical generator, what are the things you are supposed to connect to generator? Load has to be connected. Our incandescent lamps has to be connected. Our ceiling fans has to be connected. If I gift you generator, what you are supposed to do? You should connect that to fan. Right? If I give you battery, fully charged battery, you are supposed to connect it to the resistor or some kind of load. Okay. Now, for example, if I give ceiling fan to you, okay, if that in front of that fan, if you expect that particular fan should generate power, how bad it is. Okay, for all practical systems, we should know that okay, ceiling fan is there or incandescent lamp is there. For incandescent lamp, we have to supply energy. Incandescent lamp, just by taking incandescent lamp, we should not expect that incandescent lamp to deliver energy back. How bad it is. Okay, for all practical systems, forget about analysis. The analysis of all these will come later. But at least direction of energy transfer should be known. Okay, so in order to know direction of energy transfer, polarity should be there for voltage, direction should be there for current. Okay, and in the next session we will see. Thank you guys, and like our YouTube channel GATE Conqueror and subscribe to our YouTube channel, because if you do this automatically, it will make me motivated. Thank you guys, all the best.